Okay, everybody, I'd like to welcome everyone to the second installment of the 2026 Energy West Controls webinar series. I'm Matthew Copeland. I'm one of the many sales engineers to support you in the field. We will be doing a Q&A session afterwards, so please leave your questions in the chat area. I would like to introduce our speaker today with Armstrong International. Raj Nayanaraj is the North American Circular Thermal Manager. Raj integrates heat pump systems into large institutional and industrial facilities, including hospitals, universities, hotels, and government campuses. Next slide, Raj, please. Energy West Controls, we do many different things. We're a manufacturer's rep, if you don't know already. Next slide, please, Raj. We cover Mountain West, Southwest, and the Front Range. Next slide, Raj. We also do something in this territory that nobody else does. We offer steam trap surveys. We have a dedicated trap tester, and we do training, all types of training, in-house or in our offices. Next slide, Raj.
Yeah.
I'll let you start that off. Thank you and enjoy the presentation.
Thanks, Matt. Very good afternoon to everyone. In this session, I would like to share about water source heat pump. There are two types of heat pump available in the market. One is air sourced and water sourced. We predominantly focus only on water source heat pump. So I would like to share what is a water source heat pump, how to integrate that water source heat pump in an existing facility or in a brand new facility, how the efficiency of the heat pump gets evaluated. It gets evaluated with a simple term called coefficient performance. We'll see what is that. What are the challenges in heat pump design and implementation, and how to integrate it? What challenges we would face when we try to integrate this heat pump in an existing facility? Some heat pump applications and some of the case studies where we implemented the heat pump in the past. And there are different refrigerants which are available in the market. Each refrigerant is associated with certain hot water temperature. We'll see the which refrigerant can give you which temperature hot water, how it varies with respect to pressure, and how to monitor the heat pump performance. It's very, very important. Implementing a heat pump is easy, but how to evaluate whether it's really working as per the design or not. And then steam heat pump. Yes, we manufacture steam heat pump, but it comes with a certain operation challenges. We'll see what are those as well. Before I go into detail about the applications, case studies, and challenges, I would like to give a brief about what the heat pump is by comparing that with a chiller. Both heat pump and chiller works in a principle called vapor compression refrigeration cycle. Both are refrigeration equipment. You can see the same components in a chiller as well as a heat pump: compressor, condenser, expansion on an evaporator. Imagine a chiller is designed for 100 tons of cooling at 45-degree chilled water, and this chilled water goes to different process cooling or building cooling. A heat pump can also be designed for 100 tons of cooling at 45-degree chilled water. In a chiller, the compressor compresses the refrigerant only to 90 psi. This is associated with specific refrigerant. This 90 psi of refrigerant, which is compressed from the compressor, carries some amount of heat that needs to be removed from the refrigerant. So there should be a process where this vapor refrigerant gets converted into liquid, where that's the reason why this equipment is called as condenser. So a warm loop of water at 86 degree Fahrenheit comes in the condenser, removes the heat from the refrigerant that goes out as 95 degree Fahrenheit. About 1.5 million BTUs of heat from the condenser is let to the atmosphere with the help of a cooling tower. Whereas in a heat pump, we'll have a bigger compressor, and that compressor compresses the refrigerant to 200 psi. Higher the refrigerant pressure, higher the temperature. So we can heat a water from, say, 140 to 150 degree Fahrenheit, or otherwise say like 80 degree Fahrenheit to 150 degree Fahrenheit. If we compress the refrigerant to, say, 250 psi, we can heat the water to, say, 170 degree Fahrenheit. Higher the refrigerant pressure, higher the hot water temperature we can achieve. If we use this heat for a specific building heating purpose or a process heating purpose, this equipment is called as the heat pump, because we are making use of the heat from the condenser. Whereas in chiller, whatever the heat which comes from the condenser, that is dumped to the atmosphere with the help of a cooling tower. Since the compressor in a chiller needs to compress the refrigerant to a lower pressure, it consumes lower electricity. Whereas in a heat pump, we have a bigger compressor to compress the refrigerant to a higher pressure. So the work done by the compressor is more. It draws more electricity. In a chiller, the compressor gets controlled based on the chilled water set point. We typically put a set point of this is the specific chilled water temperature I need for building cooling or process cooling. In a heat pump, the compressor gets controlled based on the hot water set point. We'll be focusing on the hot water on the condenser side of the heat pump. So the compressor gets controlled based on the hot water set point. So both works in the same principle. Both evaporator in the chiller and in the heat pump can generate the same capacity. But if you see, the heating capacity is a bit different in the chiller side and the heat pump side. So anyone who operates the chiller can operate the heat pump also. Any maintenance required on the chiller, the same thing is applicable on the heat pump as well, like changing oil in the compressor in the chiller or changing oil in the heat pump. Pretty much the same. Cleaning the condenser, heat exchanger, or the evaporator heat exchanger, again, that remains the same. So I see chiller and a heat pump like a cold coffee and a hot coffee. Ingredient remains same. At what temperature we are focusing, that makes the difference. So this is the one definition of a heat pump, where it works in a refrigeration principle, where it provides simultaneous cooling and heating. Again, we are going to focus only on water source heat pump. There are many compressors are available in the market where you can use that in the refrigeration cycle to generate hot water. Scroll compressor, reciprocating compressor, screw compressor, or a centrifugal compressor. Here in Armstrong, we manufacture heat pump only heavy duty reciprocating compressor and the screw compressor. So if I have a 50-degree water, if I'm going to make like chilled water at 50 degrees Fahrenheit, and I need 194-degree hot water from the heat pump, we use a reciprocating base compressor. We use screw compressor for a bigger capacity. So this kind of a reciprocating compressor comes with a heating capacity, a maximum of like 500,000 BTUs of heating capacity, or 500,000 BTUs per hour. That's a maximum we can get from one heat pump with a reciprocating compressor. But if you need a heating capacity up to 7 million BTUs of heating capacity, then we use screw compressor, which can lift source water from 50 degrees Fahrenheit all the way up to 150 degrees Fahrenheit. This is with the refrigerant like R1234ZE, otherwise R515B. If you use a different refrigerant, say like R1233ZD, if the source water is at 110 degrees Fahrenheit, which we use in an evaporator, and we need 248 degrees Fahrenheit hot water from the condenser, so that refrigerant with screw compressor mechanism can help to lift from 110 to 248 degrees Fahrenheit. So we use two different compressor or like an industrial grade components, which is like the same design is implemented, whether it's an institutional market or an industrial applications. So let's see how to integrate this heat pump in an existing facility, or you can apply the same concept for a brand new facility as well. So imagine in a campus, they have like 4 quantities of 100-ton chillers, and that supplies 45-degree chilled water to air handling units, building cooling, process cooling in an industrial setup. So 45-degree Fahrenheit goes into the equipment and it comes out as 54-degree Fahrenheit. That runs in a common header, and that goes back to the chiller room, and the chiller processes the 54-degree water, it cools it down to 45-degree Fahrenheit, and will put back in the same loop. In the same facility, if a customer is looking for a heat pump system to generate hot water, and they're looking for like a 2 million BTUs of heating capacity heat pump, and they need 150-degree Fahrenheit hot water. So 2 million BTUs of heating capacity and 150-degree hot water. We need some sort of waste heat in the evaporator. So in the main return header, before it goes back to the chiller room, will slip a small stream of water, not the entire water, a small stream of water at 54 degrees Fahrenheit. Use that in the heat pump evaporator. This 54 degrees Fahrenheit, even though the temperature is low, it's good enough to boil the liquid refrigerant to vapor, and that goes back to the compressor, and the refrigeration cycle works. So we need some sort of waste heat in the evaporator inlet. I call this as a waste heat because when 45 degree Fahrenheit goes to the cooling coil in an air handling unit, it picks the heat from the room and then it gets heated to 54 degree Fahrenheit, and that runs in a common header. So this 54 degree Fahrenheit becomes a heat source to boil this liquid refrigerant to vapor, so the compressor can compress the refrigerant, the cycle can go on. So a 2 million BTUs of heating capacity heat pump can generate about 1.2 million BTUs of cooling, which is nothing but 100 ton of cooling. And it cools from 54 degree Fahrenheit to 45 degree Fahrenheit and will put back in the same header. If a heat pump evaporator contributes about 100 ton of cooling, and if it matches with one of the chiller capacity, instead of running all 4 chillers, we can run only 3 chillers, and one of the chiller can go off because the heat pump evaporator contributes about 100 ton of cooling. Basically, this heat pump evaporator takes small stream of water and it pre-cools it, and it goes along with the return water and reduces load on the chiller room. The primary purpose of having a heat pump is to generate hot water at a specific capacity. But this heat pump works in a refrigeration principle where we need some sort of source on the evaporator to boil this liquid refrigerant. So if we integrate that with the chill return water network, where we're taking the small stream of water at 54, it'll cool down at 45, and the refrigeration cycle can work. The heat pump can contribute the cooling in the system. One of the reasons the heat pump became trend is because for one single electrical input, it can give you 2 useful outputs in terms of heating as well as cooling. That's the only reason, one of the reasons this particular equipment became famous, because for one input, it can give you 2 useful outputs. So this is one way to integrate a heat pump into an existing chilled water loop. But there are a few challenges in it. Let's see what are those. Imagine these chillers are working only during summer, but none of the chiller works during winter. In that case, we would not get this 54 degree Fahrenheit from the chill return water because there is no load of cooling in the campus. There is no waste heat to evaporate this liquid refrigerant out. The vapor will not go back to the compressor. The refrigeration cycle will not work. The compressor will trip off. The heat pump will trip off. Even though there is a heating demand on the heating side, the heat pump will not work. So we need to know how many chillers you would operate during summer and winter. If you're going to operate only one chiller during winter, then probably it will take only half of the capacity as a waste heat for the heat pump design. That could end up only like 0.5 million BTUs of heating capacity, but that's what we can provide. So that is one challenge. We need to know what is the amount of waste heat we get during summer and winter. Imagine, so we understood that the 4 chillers operate during summer and winter throughout the year, for example. But during winter condition, this return water temperature usually drop down. Like instead of 54 degree Fahrenheit, it will be at 48 degree Fahrenheit during winter season. So when we design this heat pump, we need to know what could be the lowest chill return water temperature going to the heat pump. That should be the design base to design the heat pump. Because if I design the heat pump for 54 degree Fahrenheit, it would provide 150 degree Fahrenheit during summer. But during winter, if it's coming at 48, and if I didn't design for it, the heat pump will run, but it will never achieve the set point. You might have heard a common complaint that the heat pump struggles to work during winter season. That could be because of that. So if we know those conditions, then we can design the heat pump and provide the stable hot water temperature throughout the year. When we shut down a chiller, so there will be some cascading savings in the chiller room. If one of the chiller is switched off because the heat pump contributes 100 ton of cooling, chiller is an electrical equipment. Imagine it consumes about 60 kilowatt of electricity. That can be saved. The condenser, water circulation pump power consumption can be saved. Cooling tower fan power consumption can be saved. the water losses from the cooling tower can be saved. So even though the primary purpose of the heat pump is to generate hot water, because it integrated with the chilled water network, there will be some cascading savings in the chiller room. We'll see how to evaluate the performance of a heat pump. It gets evaluated with a simple term called coefficient of performance. It's a very simple formula. What is the electricity we feed to the heat pump? That's the input. And what's the heating capacity we get from the condenser? So if I feed 200 kilowatt of electricity to the compressor, I get about 2 million BTUs of heating, 560 kilowatt of heating in thermal units. So the heating COP becomes 2.8. Like I said, in a heat pump, you get two outputs. If I feed 200 kilowatt of electricity, I would get 2 million BTUs of heating capacity and 1.2 million BTUs of cooling capacity. So the combined COP becomes 4.6. In other words, if I spend $1 worth of electricity in a compressor, I get about $2.8 worth of heating and $1.8 worth of cooling. Again, this is the reason the heat pump became trend, because for one single input, you can get two useful outputs in terms of heating, in terms of cooling. In an electrical heater-based hot water system, imagine a filament is installed in a tank and you pass electricity and then that electrical heater heats the water. If you pass 1 kilowatt of electricity to the heater, it generates only 1 kilowatt of electricity. So the COP is 1. In a gas-fired water heater, if it's 98% efficiency, if you burn $1 worth of natural gas in a gas-fired water heater, you're going to get only 98 cents worth of heating. There's no cooling from the equipment. Same for steam boiler. If a steam boiler is 80% efficiency, that steam is utilized to heat water. When you burn fuel in the steam boiler, the efficiency of the hot water system could be like 80. Like if you burn $1 worth of natural gas in the boiler, you're going to get only 80 cents worth of heating. Whereas in a heat pump, you use 1 kilowatt of electricity, you will get 2.8 kilowatt of heating and 1.8 kilowatt of cooling. So before we when customer is looking to implement the heat pump, and if they want to have certain payback on this equipment, certain payback on the investment they do, before we do a detail engineering, this formula would be a good enough to evaluate whether the heat pump is going to provide a positive operation cost savings or negative operation cost savings. For that, we take the electricity cost from the facility and the fuel cost in the campus, multiplied by how we are generating hot water today. Is it through a steam boiler, gas-fired water heater, what the deficiency is? If this value is lower than COP, after installing the heat pump, you're going to see some savings. It could be $10,000 a month, or it could be $100,000 a month. It depends on how this value is lower than the COP. But if this value is greater than COP, after installing the heat pump would work, but you have to pay more money to operate that equipment, which some of the case where customers expecting that there should be some sort of savings after installing a heat pump in terms of monetary values, they may not get it, but the heat pump would work. So it will be a good formula to evaluate whether the heat pump would pass the positive operational cost savings or negative operational cost savings. Now we saw how to integrate heat pump on the cooling side of a chilled water network. Let's see how to integrate on the hot water side of a network. So imagine in a campus, they have steam-based hot water system where they supply steam on one side of the plate heat exchanger or shell and tube heat exchanger. They heat the water to 150 degree water, 50 degree Fahrenheit. It's a closed loop heating that goes to different air handling units in different building blocks or process area, packaging area. In an industrial setup, 150 goes in, and then return comes at 140 degree Fahrenheit, and then goes back to the heat exchanger. Now, in this campus, if they want to integrate a heat pump, this is an existing facility. If they want to integrate a heat pump, now instead of a chiller plant in the campus, I'm taking like district cooling. There is a centralized district cooling where the chilled water comes into the campus out, and this chiller room is outside the entire campus. The chilled water comes in at 45 degree Fahrenheit, and the return goes at 54 degree Fahrenheit to the um, district cooling. Now in here, if I want to integrate a heat pump, I'm designing a 2 million BTUs of heating capacity heat pump. In the main return header, before it goes out of the campus, we can take a small stream of water at 54. The heat pump is going to cool it down to 45. We'll put back in the same header. If you have a flow meter in here, and in the supply or the return side, we have temperature transmitters, you can calculate how much of cooling this heat pump has done and contributed to the chill return water network. So that one way you can do the savings calculation. So in here, we are taking the return water at 54, we are cooling that to 45 degree Fahrenheit, and we are going to put back in the same header. On the hot water side, we are going to generate 250 degree hot water. So how to integrate this heat pump with the hot water network? Depending on what the capacity of the steam-based hot water system, imagine this is also 2 million BTUs of heating capacity. The heat pump is also 2 million BTUs of heating capacity. Put an isolation valve, make two tappings, divert the entire water at 140 to the heat pump, let it heat to 150 degree Fahrenheit, and put back in the same return header. Because heat pump requires certain maintenance, like changing oil in the compressor or cleaning the condenser or the evaporator. When the heat pump is not working, you still need some heating system as a backup. So you take the return water, you heat it with the heat pump and put back in the same header. If the set point of the existing hot water system is already achieved, the hot water will go through the steam-based hot water system. It sees that the temperature is already met, the steam control valve will close, and then the hot water will just pass through the existing steam-based hot water system. Most of the pharmaceutical facilities, food processing plants, or even in a campus, um, where they want to integrate a heat pump, they would still keep something as a backup, because heat pump at times it requires certain maintenance. So this is majority of our customer base, like they integrated a heat pump in this direction. You do not need any like a complex control to control this heat pump. Like the heat pump is going to see what is inlet temperature, it will provide the hot water temperature. You divert the water, that's it. No controls required to integrate heat pump in the hot water network or the chilled water network. So it's a very easy to integrate a heat pump in an existing facility. I would like to show a case study of how the heat pump is integrated in an institutional facility to heat domestic hot water. So one of the first installation in Armstrong, we launched this product 10 years ago in Armstrong India division. Now we are making this heat pump in Armstrong Belgium, Armstrong Mexico, and then Armstrong USA. But this was our first project in a Hilton property, a 5-star property, where they have 3 heat pumps. This installation is so fascinating. The Hilton and the Marriott engineers are the one who, like the global chief engineers, started writing the specification for a heat pump in an hotel facility. And the level of trust they had on this technology is very, very amazing. This particular facility is a 5-star hotel. It's in a warm area of west part of India, but there are 3 heat pumps, 2 working and 1 standby. And there are no backup hot water heaters, electrical heaters. There is no gas-fired water heaters. There is no steam-based hot water system. There is nothing backup. It's just 3 heat pumps, 2 working and 1 standby. And it's been working for more than 6-7 years now. And hot water is a very critical element in a hotel, like whether it's for domestic water purpose or in a kitchen, or for example, in a pool heating. It's a critical element in an hotel industry. Every now and then I go there and see the TripAdvisor. Anyone has talked bad about that they didn't get hot water or not. Their ratings are really, really amazing so far. So the level of trust the Hilton and Marriott engineers had on the heat pump, it's very fascinating that there are no backup hot water system in their entire campus. It purely works on chiller and the heat pump. Like I said, this was installed in a warm part of India. They run the chillers throughout the year. So there is always waste heat load in the heat pump evaporator to generate hot water. So good trustworthy technology, where they use heat pumps to generate simultaneous cooling and simultaneous heating. So this is the typical integration we did for domestic water heating in an institutional concept. Imagine a hotel, for example, or a resort or an institutional building. They have chillers. The main chill return water header, we are taking a tapping of water at 54 degrees Fahrenheit that goes to the heat pump evaporator. The heat pump will cool it down to 44 degrees Fahrenheit and will put back in the same header. On the condenser side, we generate hot water at 150 degrees Fahrenheit that goes to another plate heat exchanger. Because in most of the institutional facility where they want to heat domestic water, they will not take this water directly to the heat pump. Because if there is any leak in the condenser for any good reason, the refrigerant and the oil in the loop gets mixed with the domestic water, which is really not good. So there is a plate heat exchanger over here. The hot water from the condenser act like a primary heating loop that goes to one side of the heat exchanger. The other side of the heat exchanger, there is a pump which takes the water from the tank. It goes on the other side. It gets heated to say like 145 degrees Fahrenheit, and that goes back to the tank. There's another nozzle which takes the water from the tank and goes to one side of the mixing wall. The other side, most of the institutional facilities, they recirculate the hot water. Even though it's a domestic hot water application, they recirculate the water. So the mixing wall takes the hot water from the tank and the recirculated water from all the guest rooms. If there is usage, the makeup cold water gets added to the tank or to the mixing wall. The tempered water finally goes to the guest rooms. So they for any heat pump, we need a tank for two different reasons. We'll see down the slides why we need a tank. But all the time, we are keeping this tank at 145 degrees Fahrenheit. And we supply the cold water when there is needed, and we supply hot water from the heat pump system. So when we keep it at 145 degrees Fahrenheit and above, the Legionella bacteria gets killed within few minutes. So Hilton and Marriott, they standardize this kind of design to keep the hot water 140 degrees Fahrenheit above, because it's stored in a tank so that the Legionella bacteria gets killed within few minutes. So this is a typical installation for heat pump to heat domestic hot water. So this is the way we have supplied the heat pump systems to the institution facility, where this is the heat pump with circulation pumps inside, and this is the tank, the three-way wall mixing station, the secondary heat exchanger, which bifurcates the condenser loop and the water loop from the tank. Typically, we get a very, very less footprint in a utility room. So we take the dimension and try to accommodate everything within a small packages. So two different packages get supplied to the site, and the contractor takes less time to install it, and they do the commissioning very short period of time. Now, so far we have seen the heat pumps, how to integrate with the chilled water network, provided the chiller runs throughout the year. It could be 4 chillers, or it could be 2 chillers, or 1 chiller at least run throughout the year. What if in a facility, if the chillers are not running during winter season at all? Then we need to go for hybrid design. We have a heat pump here where we take the chill return water, and that goes to the heat pump evaporator, and it cools it down, and that goes back to the same header. The hot water, we take it from the tank, and that gets heated, and that goes and stored in the tank. If the chillers are not running, the heat pump cannot run. So in that case, a gas-fired water heater could be a backup, or you install electrical heaters in the tank to heat the water in the tank, or it could be any other means to generate a backup heating in case the heat pump is not working. And you make this as a centralized heating plant, and you can take the hot water for any hydronic heating, or you can take the hot water and indirectly heat the domestic water with a heat exchanger package. So a place where there is no waste heat source, there is no chillers running during peak winter season, like imagine like December, January, and February. In that case, we need a hybrid heating solution. We have seen in some of the places where if they are coming up with a brand new facility and they are planning to go for like 4 quantities of chiller, and then maybe steam-based hot water system or electrical heater-based hot water system, instead of going for like 4 chillers separately and then 2 steam boilers or 4 gas-fired water heaters for heating and then simultaneous and chillers for cooling. If we know during the design stage, if we know what is the heating load and cooling load, simultaneous heating load and cooling load, when we know that, instead of going for 4 chillers, we can go for 1 heat pump followed by 3 chillers, because the heat pump can generate chilled water as well as hot water. So make this as a parent equipment to provide cooling. If the demand goes higher, then we can switch on our other chillers parallelly in the system. So as we have seen this trend, like many of the new resorts or institutions where they have to go for multiple chillers and then multiple heaters, once we know what is the balance load on the heating and cooling side, then we can integrate this heat pump in this direction. Not all chillers can be replaced with the heat pump, because it's very, very rare that in a campus, the heating load and cooling load matches all the time. Maybe 1 or 2 chillers can be replaced with the heat pump, depending on what is the simultaneous heating and cooling load in the facility. So far we have seen using chilled water as a source in a heat pump to generate hot water using, like, if we use screw compressor, we can achieve 160-degree hot water. If we use reciprocating compressor, we can achieve up to 194-degree Fahrenheit. But there are other waste heat source. You can use that also, like sewage water, wastewater, or any kind of a geothermal application. We can use the waste heat from this in a heat pump to generate high temperature hot water. In a facility, if they have a cooling tower and that temperature varies between 86 to 95-degree Fahrenheit, we can use that in the heat pump to generate higher temperature hot water, maybe like 180-degree Fahrenheit using screw compressor and 194 using a reciprocating compressor. If we get even more higher grade waste heat, some flue gas exhaust from a boiler or an industrial dryer or CHP, packaged CHP unit in a facility, if that waste heat temperature varies between 100 to 194-degree Fahrenheit, we can use that in the heat pump to generate hot water all the way up to 248-degree Fahrenheit. So far we have seen chilled return water as a source. Now we'll see some other waste heat, how to use that as a source in the heat pump to generate hot water. So the first one is cooling tower. Imagine an industrial setup, like they have air compressor. If those air compressors are water cooled, like 86-degree Fahrenheit comes in the heat exchanger that cools the compressor, or it recovers the heat from the compressor and 95-degree Fahrenheit goes back to the cooling tower. We can divert the cooling tower return water before it goes to the cooling tower. We can divert to the heat pump at 95-degree Fahrenheit. Heat pump is going to cool it down to 86-degree Fahrenheit and will put back in the same header. Depending on the evaporator capacity, the load on the cooling tower goes down. And on the condenser side, we can generate hot water all the way up to 175. In certain cases, we can go up to 180-degree Fahrenheit also. So take the chill return water, cooling tower return water, like the way we saw that in chiller. Take the cooling tower return water, use that in the heat pump evaporator as a waste heat source, and generate 175-degree high temperature hot water. So in a facility where there is only cooling tower, you can still use the cooling tower water as a source in a heat pump to generate higher temperature hot water. In a university campus, like science building in a university campus or a medical center, healthcare center, research labs, R&D centers in a pharmaceutical facility, where they have an air handling unit, they bring 100% outdoor air, they condition it, that goes to the rooms, and there is a centralized exhaust which throws the conditioned air at 65 or 70-degree Fahrenheit outside the building. So if there's a centralized exhaust, which throws 70-degree Fahrenheit conditioned air out, we can have a small plate fin coil, like a radiator coil, run a low temperature water loop from the heat pump evaporator at 45-degree Fahrenheit. That will recover the heat from the 70-degree air, and then it becomes 54-degree Fahrenheit. It could be a glycol loop or water loop that goes to the heat pump as a heat source. And then on the condenser side, we can achieve 150-degree hot water that can be used in the same air handling unit if the heating coil is like a hot water coil. and then we can use the same hot water in reheat coils, or we can use in a centralized hot water loop. So in a university campus, before you change the central heating plant from steam to heat pump or any other technology, if you work backwards, like you have many centralized exhaust, you start recovering the waste heat and take the hot water return, the hot water from the return header, you take it in the heat pump, you heat it and put back in the same header. So the central plant heating load will go down. So instead of changing the central heating plant in a campus from steam to a steam-based hot water system to heat pump system, if we can work backwards like each building and then reduce the load in the each building with the help of a heat pump, definitely your central plant heating load will go down. So this is one of the application I really like, because heat pump likes to see a consistent waste heat. And here we are getting like a consistent waste heat from the exhaust. Whether it snows outside or 100 degree Fahrenheit outside, it does not matter. We get consistently a 70-degree warm, not a warm air, conditioned air in the exhaust, and we can recover the waste heat, use that in the heat pump to generate hot water. So this is another application where we can integrate a heat pump with a centralized exhaust system. In a facility where they have a packaged CHP unit to generate their own power, if there's a dry cooler which throws the waste heat, typically a glycol loop or water loop runs between the packaged CHP unit and the fan cooler. We can divert the water or glycol at 130 degree Fahrenheit to the heat pump evaporator. It will cool down to 120 and we'll put back in the same loop. In case the heat pump is not working, your fan cooler will still cool it down. And on the condenser side, we can achieve hot water at 180 degree Fahrenheit, and you can use for any kind of a heating application in the facility. So this is another application where you can integrate the heat pump using the waste heat from a packaged CHP unit. In certain facilities, a boiler cannot be replaced at all because they need a higher temperature, higher pressure steam. So they would be still using the steam boiler. But if the makeup water is preheated with the help of steam from the boiler, we have seen in certain facilities where they heat the makeup water with the help of the steam from the same boiler. Instead of doing that, if there is any waste heat near to the boiler house, you can have a heat pump, make use of the waste heat in the heat pump evaporator, and use a condenser to heat the water from say like 50 degree Fahrenheit all the way to 194 degree Fahrenheit. So the heat pump technology can preheat the boiler makeup water to a higher temperature instead of using steam from the same boiler to preheat the makeup water. So this is another application where we can integrate the heat pump to preheat the makeup water from 50 degree Fahrenheit to a higher temperature. This is one of the very fascinating application where we have seen this project was done by our technology partner in Germany. They've installed this heat pump 40 years ago. Even though industrial heat pumps are like a new trend these days, but the heat pump topic lived for so many years, and they use river water as a source. So this is a hydropower plant where there is a river water nearby, and then they generate power for that specific city or the district. So there is no chiller in their campus and no cooling tower. So what they did, there's a river nearby. So they made two pits, pit number 1, pit number 2. By gravity, the river water flows to the pit number 1. There's a pump which pumps the water from this pit to the next pit. And they put a pillow type heat exchanger in this pit in a specific pattern. So the water comes from this pit to this pit. The water flows in this direction. It takes a U-turn and then it goes back. Some portion of the water is recirculated back and some portion of the water goes back to the river. So in here, they recover the heat from the river water and use that as a waste heat source in the heat pump, and they generate hot water that gets stored in the tank for domestic water purpose or like an hydronic heating during winter season. And these units have been working for more than 40 years now. You might have heard that the chillers work the chillers have a life of like 20 years, 25 years, or even 30 years. The heat pump works in the same principle. Only the compressor is of bigger size, more power. But if we can maintain this very well and designed it correctly, and it can work for years and years. The good thing about this customer is that they did preventive maintenance for 2 times in a year, last 40 years, and then it's been working for more than 40 years now. So this is another way. If a facility does not have any kind of waste heat, river water can be used, or imagine like any kind of geothermal heat can be used in the heat pump to generate domestic water or hydronic heating water application. Another project which our German technology partner did is waste heat from sewage water. This is Stuttgart city in Germany where they want to build a new district in this area. They have two options as a waste heat. One is river water and the sewage water. There's a sewage canal which runs in the middle of the city. So they have two options, whether to recover the waste heat from here or from the river. So the project they did is to recover the waste heat from the sewage water. So this is the centralized sewage canal, and this is the new district where they built commercial buildings, residential units, and sport complexes. So in the sewage canal, there's a cross-section view of it. They install a heat exchanger. They run a glycol loop inside this heat exchanger. They recover the waste heat from the sewage water because based on their study, the sewage water temperature varies between 68 degree Fahrenheit to 50 degree Fahrenheit. So they recover the waste heat from the sewage water. They fed that waste heat in the heat pump. Heat pump generates hot water, and that goes and stored in the tank, and it goes to the different applications in the same district. So this is the heat exchanger, the design, and this can be installed like routed through a manhole, and then it's installed on the bed of the sewage canal. And this is the heat exchanger where they run a cold glycol, and the glycol runs between the plates, and then it comes out here. The sewage flows on top of this on this heat exchanger. So the cold glycol recovers the heat from the sewage, and that waste heat is fed to the heat pump. The heat pump generates hot water that gets stored in the tank, and then it's pumped to the nearest district. So this is the heat exchanger where they pass the cold glycol, and it passes between the plates, and then the warm glycol comes out of this heat exchanger. These photos were taken during the installation phase, so it's little bit there is no sewage water flowing on the heat exchanger, but you can get the idea that the sewage water flows above the heat exchanger, and the glycol loop inside the heat exchanger picks the waste heat from it. So this is another way you can recover the waste heat from a sewage water. And it's not necessary that this needs to be a new canal. Even if it's an existing canal, the heat exchanger manufacturer can provide a customized design, and you can drop through the manhole and install that in the sewage canal. So far we have seen different waste heat sources, different case studies, how to use that in a heat pump to generate hot water. We manufacture high temperature heat pump which generates hot water up to 248 degree Fahrenheit. There are 4 of these heat pumps installed in a Cargill facility, a food processing plant in Norway, and it's been running for more than 4 years now, where they take this hot water in an industrial dryer to dry pet feed or aqua feed products. And this uses R1233ZD as a refrigerant, and that is used in the refrigeration cycle to generate hot water up to 248 degree Fahrenheit. The only challenge is that in order to run this refrigeration cycle, we need a waste heat at 110 degree Fahrenheit and above. We cannot use chilled water directly in this heat pump to generate high temperature hot water. So we make packaged unit where everything is assembled, tested from our factory, and then ship it to the site. And like I said, there are 4 heat pumps installed in a Cargill facility to generate hot water for an industrial dryer application. And this will be a pressurized hot water at 248 degree Fahrenheit. So since we make 248 degree Fahrenheit hot water from a heat pump, where the source, like I said, we need a source 110 degree Fahrenheit and above, we can make 248 degree hot water. If we can flash that in a flash vessel, we can make steam up to like 10 psi of steam. And this steam, you can put in a thermocompressor. Imagine there is a district steam available near to the campus. We can take a high pressure steam, maybe 150 psi or 200 psi, use that in the thermocompressor to compress this 10 psi of steam to 50 psi of steam. Or you can use steam compressor, the MVR, mechanical vapor recompression compressors, to boost it from 10 psi to 50 psi. But the challenge in this kind of a system is that whatever the steam this heat pump generates, at least bare minimum 50% of the heat needs to be consumed somewhere in the process. Could be direct consumption or an indirect heating consumption. So the load should be utilized. It cannot be installed in an application where there is a heating application only for 3 hours and then the remaining 6 hours it's going to be idle. In that case, imagine if the heat pump is switched off and all the steam in this line will get condensed to liquid, and then the vacuum gets generated in the flash vessel. It pulls the air inside it. Now you have got cold condensate inside the flash vessel that will react with the non-condensable gases. It becomes carbonic acid and it starts eating the equipment. So as far as you're utilizing the steam consistently somewhere, at least 50% is the load, then this heat pump system could work really well. But if you're going to use in a batch process, starting at the heat pump would be as good as starting a boiler. So you need to wait like 10 to 15 minutes to start and generate steam. And most of the application will not wait for that. So as far as your heating application is consistent, then this kind of system could work out really well. For any heat pump, in most of the application, you have seen a tank. Heat pump needs a tank. If the hot water demand is going to be, it goes to a batch heating process. If the load swings a lot, then you need a buffer tank in here, because the biggest misconception most of us have is considering heat pump as an instantaneous hot water heater. Heat pump is not an instantaneous hot water heater, because imagine the heat pump provides hot water and then it goes to a specific heating process load. If there is no load, the heat pump understands that I should not generate any hot water, and then the compressor trips off. If the compressor goes off, it takes 3 to 5 minutes to switch back on. So it's very important that we need to know how the heating load swings. If it's going to vary a lot, it's better to have a buffer tank for two reasons. One, to store at least 5 minutes worth of thermal energy in case the heat pump is not running. The second thing, this tank will provide a stable return water temperature going back to the heat pump. That will keep the heat pump healthy. So for those two reasons, we need a buffer tank. And whenever for any kind of heat pump project, we do the engineering for the complete engineered package, and we stand guarantee on the performance of the complete system. And we monitor the COP, and it will be published on the HMI on a real-time basis. What's the heating load, what's the cooling load, and what the heat pump COP. So on day one of commissioning, if you're not going to see the COP, then there should be two reasons. One, the design is wrong, or the input provided is different than the day when we are commissioning. So anyway, it will be very much evident. If the design is not good, you will see definitely a different number here. Every decimal in the COP is worth thousands and thousands dollars worth of savings. And if you have committed that you will get the entire money within 3 years, and if it's not 4.8, it is actually running at 3.4, we are not going to get their money within 3 years period of time. So it's a good tool to evaluate a manufacturer like us, whether we have done the design correctly or not. So the final slide. We manufacture heat pump. The smallest capacity is 150,000 BTUs. The maximum is 7 million BTUs of heating capacity. We manufacture heat pump which can make hot water all the way up to 248 degree Fahrenheit. We make all custom built heat pump. You define the capacity, you define the part load condition, you define the dimension. We will try to accommodate everything within one skid and supply to the site. And we make these heat pumps in Michigan. That's all I have from my side. If you have any questions, I can answer it.
Thank you, Raj. If there's any questions, put them in the chat. We will answer them. I did get a text from a client, installations in the US.
We have two installations, one in Oak Ridge National Laboratory in Tennessee for a 230-degree Fahrenheit heat pump that is under installation now. And there is one more 175-degree Fahrenheit heat pump installed in Georgia power plant that will get commissioned in the month of June, in next month. Um, and we have one
Fantastic.
in Mexico City in Mexico in a chocolate plant where that heat pump provides simultaneous cooling and heating, and it's been running for more than 4 years now.
Fantastic. Any other questions? All right. We'd like to thank you all for attending. And you can, if somebody missed this, you can go to our website and watch this recorded webinar. Thank you, everybody, and have a great day.